Started. Okay. So the next thing we're going to be talking about is a very substantive topic, and that's all about the state chart issues. We're going to be introducing, ladies and gentlemen, so we're going to be introducing state charts now. We've seen them informally, but I want to introduce them in a somewhat more systematic manner. Okay, and we're in a Bach-like fashion, fugue-like fashion. I'm going to be having us build up a model which uses state charts from the get-go. Okay, so frequently we want to capture agent behaviors transitioning between different states that are discrete, categorical often. They're mutually exclusive, collectively exhaustive states, for example, associated with weight categories, or associated with income deciles, or associated with cities in which they live, or what have you. And we can characterize those transitions using state charts, okay? In a simple state chart, and we'll talk about elaborations of this, an agent is in exactly one state at a time. And there's some transitions between states that define the paths of evolution. These transitions between states will occur based on some condition, and we'll see we can define a number of conditions. And when they occur instantly. You're not in the transition for a certain amount of time, but you go across that transition from one state to the other at a certain moment in time. You switch states. Okay. So I'm going to actually ask you to build up a little model here, and we're going to rehearse these skills that we've been applying. So with your leave, I'm going to close this model that we've already built, and we're going to create a new model. Mind you, these models have made models available of the sort I'm planning to build on the Dropbox site. So you can always go and open them up, even if you had some issues with your model. Let's create a new model, okay? And let's create a model that's called simple interacting weight and diabetes state charts. I'm going to be pressing the envelope a little bit with this because we're going to be defining two state charts, one for weight and one for diabetes status, because I want to show you how you can have them interact. Okay. So, ladies and gentlemen, a new model stands before you here. I did File, New, Model, and I named it this: Simple Interacting Weight and Diabetes State Charts. By request, I understand it's hard for people to see in the back there. Let me go. Oh man. Sorry, I want to get a nice new thing up here. Come on. Boom. There we are. That's what my name for it was. You don't have to use it if you don't want to. Okay. So here's a model. Suppose I want a population of people in this model. Tell me what I have to do. Okay, new agent type. Excellent start. So, File, New, Agent Type, and let's call it Person. In general, we give names to so-called, these are what we call classes. They're kind of like the molds we use to bake cookies. A given mold, it describes the shape of the cookie, describes the properties of the cookie. These describe personhood. And then there's many particular cookies you make from that mold, right? You make many cookies from that cookie mold. And similarly, this person class, personhood, then applies to many of those particular people circulating in the population. Maybe it's 10,000 people in your population. But each of them is basically described by the personhood as defined by person. So when we define these classes, we capitalize them by convention, okay? Okay, so suppose we wanted to give these people an appearance. How are we going to do it? Suppose we want to make them a circle. How do we do that? Sorry? We want to make these people a circle. How do we make them appear like a circle? Okay, palette, presentation, and then what do we do? Okay, and we do what with it? Drag it in here. You know, I like to resize it so it doesn't occupy too big a space here. You know? Boom. There you go. Okay, so each person is there in a with a circle appearance. Okay, now what do we want if we want a population of these people? Where do we go? Where do we go to create a population of these people? If we run the model now, are there lots of people? If we run the model now, what will we see? We'll see nada, nothing. So what do we have to do to make there be see something? Okay, we have to. We define personhood. What have we not yet done? We need a population of people in Maine. We need them to be living in a population. Right now there's the potential for personhood, but there ain't nobody to be a person right now. So how are we going to create a person? How are we going to create a population of people? What do? Drag a person into Maine, and we call it population. These are basic skills that we're rehearsing. The theme of the fugue has reasserted itself. Okay, so we want a population of agents of size 100. We could create a population size parameter again, but for interest of time, we'll leave it as 100 now. Great. Okay, let's run the model. What will we see now? Well, we'll see there's 100 people, but they all look the same. Suppose we wanted to spread them out across the field. We want to spread them across the campus. How do we do that when we run it? Rather, spread them out when we run it. How do we do that? Who controls their position by default? Maine. Maine is where they live. Maine is where the population is. So we're going to, within Maine, we'll go down and we'll set the layout type to be random. All I did is I went to Maine and I scrolled down in properties till I get to this area and it says layout type random. Who needs TA help? TA help? TA's spring into action from the back. Okay? Good. Thanks, Kurt. Okay, so we want random. Okay, who else needs help?
Okay, so created person, right?
Yeah.
You did two, right?
Yeah, I did. Created person. I've done debugging something else in the past.
Okay, there we go. Do you see that? Who needs professor help?
So click this little thing.
Okay.
Option, so that comes in.
Okay, so folks, let's rehearse what we've done thus far. We went in, we created a person class, we gave it a nice little circle. We went into Maine. We dragged in person to Maine, create a population. We marked the population as a population of agents of size 100. And then we went to Maine, we scrolled down, and we set it to be a random layout type. And that has lent itself to this nice presentation. Okay? Okay. So, ladies and gentlemen, shall we press forward? Okay. Okay. So, that looks good. But we don't need a parameter yet. Let's go over to main. Yeah. Okay. You want to go? Let's go over to project. So you want to drag person to here, and you want to call that population. Let's delete that circle. And you want to make it a population of agents here of size 100. You got it. Okay, don't worry about that. And now go to main. Main, yeah. And then let's go scroll down. And you just set this guy to be layout type random.
And how do you make that not one?
Okay, good. I think you're good to go. So run, save, run. Yeah, good. Okay, good.
No,
Excellent.
you were right
Okay,
there.
oh, they need an appearance. I'm sorry. Okay, here we go. What is this? There we go. Okay, double click. Okay, give them a nice appearance. Palette. Give them go click here, and then drag this round, this oval over there. You could just drag this guy. Yep. Put him up there. Good. Okay.
That's all I see there.
Yep. That's all you see. Okay. Okay. So, folks, we should see this. We just rehearsed the basics. This is what we see. Do you see that, Lisa? Do you see something? Oh no. Kurt, could you take a look at this? Let's go back to projects. Go to main, double click main. Population size 100. Yeah, she has that. She's seeing nothing. Okay, go click here. I think it was because she added the thing after the fact, maybe.
You have to
do recreate.
Yeah. So can you go back to main?
Okay.
I think I need to do that anyway.
Yeah. So you can remember where that would be in the environment.
Okay. So,
delete this.
Okay.
Drag it in again.
Okay, yeah, there's actually another way to do it too. Okay, there we
Now
go.
you have to do this.
Yeah, folks, if you modify a person after you've created a population of it, you'll sometimes not have it know about the new appearance of person, and there's some way to get it to sort of recreate the presentation for that, but that will sometimes cause a problem. If you add the oval after you've created a population, you can easily drag it and create a new population instead, and that will be fine. Okay, so here we are. We're at this place. We have a population of agents spread out here. Okay, are we all in sync here? Who needs Windchill help? Okay, so having gotten back to this point, I just want to rehearse those basic steps. Add a person class. Add properties to that.
Thank you.
Create a population of them, and have that population laid out randomly. Now we're going to do something different. That was what we did before. Now we're going to do something different. We're going to add a state chart. We're going to give every person in this population a characteristic. Okay? So let's go into person, double click on person, and we're going to add in elements of state charts. So we're going to go down to state chart palette down here. If any of you don't see that for some reason, you can do this plus down at the bottom. And now I'd like you to drag in a state chart entry point, and it's going to be called weight state chart. Okay? So what did I do? I went down here to the palette, I went down here to state chart, and I dragged in state chart entry point, and I call it weight state chart. I'm now going to add a state in, and I'm going to make sure it gets connected with this. The state is going to be normal and underweight. I'm going to spell that out on the big screen so that you in the back can see it, like that. Normal and underweight. Notice the so-called camel case conventions with capitals between the words, normal and underweight. Okay? Okay. Next, I'm going to add another state, and this is going to be called overweight, and another state that's going to be called obese. Okay? And I'd like you to add transitions between these, just like this. Boom. And then we're going to have transitions back, because you can, thankfully, it's not a one-way street. We're going to add transitions back here so that people can go back from an overweight state to a normal weight, etc. Okay, just like that. Okay? So we built up a little state chart here. And what I'd like to do is I am going to add, so first of all, let's test this model. I do build here, and it's happy. And ladies and gentlemen, I'd like to run this model now. Who needs TA help? The TAs stand ready. They sit ready for you.
Did you put any times on the delay?
No, I'm just, first I'm not doing that. Okay, let's run it. What's that?
How do you get the arrow to go up?
Oh, how did I get the arrow to go up? I'll describe this. So it's a good question. So ladies and gentlemen, a few tips with these arrows. So they come in upside down. So I like to drag them kind of like that, and then I just drag up one side. The other thing is you want to make sure it's green where it connects. That means it's a good connection. If it's hanging, if it's like this, it'll give you no shortage of grief. It actually says it's okay, but it will cause lots of problems. But you want it to be green on both sides. Green is good.
And
Yeah.
why some of them have the clock thing on
The clock thing is telling you that's when a transition will occur. It's telling you it's a timeout transition. This guy is just the entry, so he occurs immediately. He's not waiting for anything. This thing will occur one time unit after you've entered this point. That's why it's called a timeout. So it's a different type of transition. This is a transition in immediately. This is a transition that occurs after a certain amount of time.
But did you do something to make it show?
No.
Oh, because some of them, not the main one,
Doesn't have a little clock.
yeah.
Okay.
Yeah.
That's
So did you do something to make it show?
that's no. That'll be interesting. Maybe that's something Winchell could look at. Just I don't think it's a problem, but I just want to verify. They're having the clock appear with some of these and not others, which suggests that maybe some of them are not timeout transitions. It doesn't matter that much, but
I just moved
Oh, thank you. Yeah.
oh,
Just because the
oh, you mean like if they're next to each other, or
Yeah, the yellow.
Yeah.
Depends on the arrows.
oh, I see. Okay, you mean like this?
I just moved it and then it's locked. Yeah.
I see. Okay, that's great. Okay, thanks so much. Okay, great. So let's run this. Let's go run this model. Again, good practice. Compile often. So build often, build early, build often, and then run often, run early. What do you see happening there?
I have an arrow.
Okay. So I stand ready. So what's the arrow? Okay. And then let's do run. Oh, you know what? There's a little thing here. I think it's. I think you want to see your problems window. Aha. There. I think they're not some. Oh, I see. You need the entry point here. Because there's an entry point. You just need to add the entry point from your palette. So, this guy here. Drag that over.
That's mostly just saying this is the state that everybody starts at.
Yeah, that's right. That's telling where it starts.
It's pretty much just pointing to number one.
That's right. Although in many cases we'll use that initial state. Ben, is it? Yeah. We'll use the initial state and we'll put a branch on it so that, like, if we want the initial population sum to start normal weight, overweight, and obese, like for if we have some empirical data and we want to match the distribution, we can have this branch. In fact, I was mentioning it to you earlier, and that initial state can branch. So 50% go this way, 20%, and 30%. Does that make sense? Yeah. So it's not always just one state it goes to. Okay, so folks, when we run this model, you should see something like this. Here we have nothing apparently occurring visually, but if you run it, you should see things going on. What do you see going on? A given person is changing state over time. They're going between normal and underweight and going back and forth between them. So they have some behavior. Let's make that behavior manifest. Let's make it visually obvious. Let's make their color change based on their weight. Okay? Let's make their color visually change based on their weight. Is that okay? Okay, so ladies and gentlemen, I'm trying to expand your repertoire here, not expand your confusion here. But this ain't called a boot camp for nothing. So let's go over to this general tab, and what we're going to do is we're going to add in a variable, and it will be called their color. Okay, this is going to describe the color you want to use to color them right now. Okay, and for normal and underweight, we're going to make their color be green. Okay, do you remember this capital names? So, ladies and gentlemen, I added a color. Oh, I forgot to tell you. I'm sorry. When we add the color, this is important. We add the color. We have to tell it it's not a double. It's not an int. It's not like 3.5. It's not like 2. It's not yes or no. It is something that's a color. We tell it capital C-L-O-R, just like this. We spell it differently in Canada, but this is for the American convention. Color. So how did I do that? I went to this variable and I set it. I said type other and I said it's a color. Okay? Is that okay, folks? Okay?
Question?
Yes, question.
Is there a reason why the variable has a lowercase, a color?
Yeah, this is kind of their current color. Capital C we use for to describe sort of color hood, and so in general in our models, and in fact in Java, when we give something like to describe color hood, we call it a class. Okay, so we have a class called person, and we give it a capital P. A class called main, we give it a capital M. A class called color that describes sort of color hood or colorness, describes colors in general. We give it a capital C. Okay, and that's why this is a capital C. This is an example of a capital C color, just like a particular personal model is an example of a person. It exhibits personhood as defined by capital P person. Does that help at all? I apologize. It's sort of, this describes the general concept of personhood with a capital P, and then there'll be particular persons. And if we had a particular person, we call them with a lowercase p by convention. It's just a particular person, whereas capital P person is like describing personhood, personness. Does that help a bit? Yeah. Okay, and so this is describing colorhood, colorness, capital C. Okay? Okay. So ladies and gentlemen, let's make the initial value of this black. We're going to have everyone appear initially black, okay? And let's go, how would we make their appearance? How would we make their appearance on the screen, their circle, the value of color?
Appearance?
Sorry? I hear a good thing.
It's not appearance.
That's the appearance of this circle. What would you do to make that, to make the circle appearance? How do we tell it what color to be?
Click on it.
Click on it. Okay, that's a good start. That's a great start, in fact. And that gives us all the clues we're going to need. Okay, now where do we tell it what its color should be? We've seen it before.
Fill.
Okay, fill color. How would we tell it, make your color whatever color is, the color variable? Well, we have to tell it it depends on the value. What would we type here? I'll give you a hint. It begins with a lowercase c. It ends with an R. Color. Thank you. Thank you. That was a quick game of hangman. Okay. Okay. So color. The fill color is given by color. Remember we did this before, folks? Remember we actually wrote something there? Yeah. If sex equals male, then make it gray. Otherwise, make it yellow. Remember that?
Oh, yeah.
Yeah. So it's the same idea. We just make it color. Okay. So what do we expect to see if we run this right now? We see everything is black because we've set this to be black. So let's do that. Okay, watch this. It's all black. Eh? Okay, that's good. Now, ladies and gentlemen, that may seem singularly simple. after all, we could just specify black. But now we've set the stage. We've laid the groundwork. We put out the red carpet for interesting things to happen. Suppose when they're in normal underweight state, we want their color to be green. Tell me what to do. We want the color to be green. We want to assign a value green to the color. And then we have to put the semicolon after it to appease the Java gods.
Why don't you use the fill color? Why is that default?
Well, I'll show you why in a minute. Okay. Color equals green. I see what you're saying. Yeah, it would be a nice thing to do. That, in fact, that's one of my suggestions when I talk with the AnyLogic president next
So that
month.
means it's not happening.
Version 7.5 maybe. Okay, that would be a nice thing to do. I agree completely, Lisa, and I will take your suggestion to the corridors of power. Okay, so let's for overweight make the entry action here. So this entry action is something when we come into there, we're going to do something. We're going to assign green to be the color to be green. Here we're going to assign the color to be yellow, and then we're going to assign the color to be, for obese, we're going to assign the color to be red. Okay? Boom. There we go. So what did I just do? I have this variable color. It was originally set to only black. Then I'm here saying, okay, when you come into the state, make my color green.
So look at lime.
Okay. Oh, it says lime, doesn't it?
Yeah. Maybe that does work.
Maybe I don't know. There's green, I guess. I like the lime better, but we'll leave it like that. Color equals yellow for this one. Notice you have the semicolon. The semicolon tells you, hey, I'm done with this, telling you what to do here. And you got to put that in. This is what's called a statement. It tells do something. Those things we had before, like if we're male, then use this, otherwise that's called an expression. It just computes a value. This actually tells it do something, so you have to put a semicolon after it, okay? Wherever we tell it to do something, in general, we have to put a semicolon. And then here's color equals red. So ladies and gentlemen, what's going to happen when we run this model? Riddle me that. What do you think will happen? Okay, they're going to change colors. Why are they changing colors?
They're confused.
well, there may be some truth to that, but they're changing colors because they're going between these states. When they come into this state, they become green. Why are they becoming green? Because we've assigned that to color, and this thing says, hey, whatever is used for color, used for my actual fill color. And then when they come into this state, they turn yellow, and so they switch colors. That's great, but why are they all turning green and yellow at the same time in this sort of hideous sort of regularity? Why are they all turning at the same time?
Because that's how you have the clock set.
That's how I have the clock set. That's what these little clocks mean. So these are a timeout. So you leave here after exactly one time unit. You leave here after exactly one time unit. There's no chance. There's no room for chance here. You're not leaving anything to chance. So let's change that instead to a different type of transition. Let's change it to a rate transition. Now, a timeout says after exactly this time go. A rate is more like, I don't know how many people here have done survival analysis. You talk about a hazard. You talk about a hazard function. It's a probability density. It's a chance per unit time. You'll say undergo mortality or develop a certain morbidity or what have you. This rate says there's a certain chance per unit time that you'll go from this state to this other state. And you have a certain kick at the can, and it's in continuous time. Your time here is going to be exponentially distributed. You have this, it'll be e to the minus 1 times t in this case. A rate of 2 would mean that you have even a higher chance per unit time of going. On average, you'd stay, half a time unit. Here on average you'd say 1 time unit. This was 0.1. On average you'd stay 10 time units, 1 over 0.1. The reciprocal of the rate will tell you how long you stay in at on average. So with a rate of 1, you're going to be here for the same average length of time as we've just seen, but some people will leave sooner and some people will leave later. So ladies and gentlemen, let us run that with a rate. And what we see instead is something like this, which looks somewhat less confusing. So here they're blinking. If it were red and green, it would look like Christmas in Beverly Hills or something. But here we see it kind of blinking with the colors of Saskatchewan, in fact. Okay, so you'll notice, by the way, that the icon of this changed. It changed from a clock to this thing that shows an exponential distribution, because the time in there is exponentially distributed. Okay, so this is memoryless. It doesn't matter how long you've been there, you'll leave at exactly that time. If we had a timeout, it's not memoryless. In fact, it's quite the opposite. How long you stay in there depends totally on how long you've been there. And you're going to leave in exactly 1 time unit. Okay, so here you're leaving on an average 1 time unit, but some people are leaving sooner, some people later, and hence this kind of cacophony of states here. Okay, but let's change this. Let's make these rate transitions. Maybe we'll give them nice names. So this would be becoming overweight, and we could do show name here and take that name around, and then here we can have a losing shedding overweight, something like that, shedding overweight, right? And we'll make that a rate transition also of well, let's make it's harder to lose weight than it is to gain it, so let's make it a rate transition of rate of 0.1. Going from overweight to obese, let's say becoming obese. You should have shown that last one. We'll show this name. We'll rotate it around, and this will be a rate transition of 0.2 or something like that. And then we'll have a shedding obesity with a rate transition of 0.2, something like that. Okay, so we've just changed these to rate transitions. You're not strictly limited to fixed numbers here. You could actually have, for example, the rate you use be a variable. You could even have it change over time if you're careful about it. Similarly, the timeout, how long it takes if we have a timeout transition, we could actually draw how long it is they leave. And this is an important point, pursuant to Ben's question earlier. We could have a timeout if we wanted one, where the amount of time you spend in that state is drawn from an arbitrary distribution. We could draw how much time you spend in a given state from a beta distribution, or from a gamma distribution, if we wanted to set a particular sort of distribution of time that people spend in that state. We can do that very readily with a timeout. We just draw a value here instead of using a constant. Okay. Similarly, with a rate transition, you don't have to specify a rate constant. You could just make it a, and I'm going to actually make this becoming overweight with a rate of 0.1 as well. Okay, or say 0.05. Yeah. There we go. So if this were a rate transition, we could make this depend on a variable. We just have to make sure it realizes if that variable is changed. And there's a bit of finesse to that, but you could have a self-transition here. It'll wake up periodically and realize it. Okay, so ladies and gentlemen, let's run this. So now we've changed these to these various distributions, and you should see something basically a bit like this.
Okay, what was your shedding overweight?
Okay, the shedding overweight, and this one was here is 0.1, and I'll show the name there. It's 0.1 is the rate, shedding obesity, I should show the name, and its rate is 0.2. Okay? Again, there's nothing specially privileged about constants here. We could use arbitrary variables. Okay? And let's run this thing now. And here we go. And we can see something along these lines. Now, ladies and gentlemen, I have ulterior motives in giving some of these lectures because I like to weave in additional things. How many people here would like to see how you compute statistics in a model like this? Like how many people are overweight, obese, or normal weight? You want to do that? Yeah. Okay. Okay, so ladies and gentlemen, we're going to take, I like weaving these things in. So let me show you how you can do that really easily in AnyLogic. Okay, AnyLogic. So go up to main, double click on main, because you may be wondering, well, pretty pictures are nice, but we want to report on numbers here. Okay, so go to the population. If we want to compute statistics about the population, pursuant to Gill's question, we would actually associate those statistics with the population. Okay, so go to the population, and we can do add statistics. Okay, so we're going to do fraction obese or something like that, or we could call it prevalence of obesity if you wanted to do that, right? Prevalence of obesity. Okay, so again, I went to population in main. I had to open up the main canvas, double click on main, went to population, I did add statistics, and I did prevalence of obesity, and I want to do here an average here. Okay. Actually, I'm gonna do a prevalent case count here of that, and we can actually do a fraction in another minute, which will be slightly more confusing. But so the prevalence of obesity, I'm going to count the number of people that are obese in our population. How do I do it? Well, whenever you see this little light bulb here, it indicates you have a chance to do that. So I'm going to say item. That means the person I'm referring to, dot, and it's called weight state chart. How did I get this to complete it? I did control space. It completed it. And I'm going to say, I'm going to count them as being obese if they're, how would I tell? If I looked at a person, how would I tell if they're obese? Can anyone tell me? What would I see visually if they were obese? Okay, they're red and they're in this state, right? They're in the state called obese. So what we want to do is we want to say, we want to ask, are they in that state? Weight state chart is state active, and we're going to say the obese state, okay? But we actually have to say person.obese because it's something that is a characteristic of person. That's an unfortunate thing. But you have to say it's obesity with respect to person, not with respect to a dog or a deer or a something else. So person.obese. Okay. So let me put this up on the big screen so those in the back can see it. This is what we have. Unfortunately, it's wrapped it. I'll see if I can make it a little bit bigger. Make it a little bit smaller. Font 24. Okay, that's what we have there. Item. Who is item? That's the person. Say, for that person, hey, your state chart. For that person's state chart, that's item.weight state chart. That's the state chart for them. And I'm saying, hey, state chart. Yeah, you, the state chart. Is this certain state active called person.obese? Is your state active? Is this particular state active? Are you obese? Yes. If so, we're going to count them. Otherwise, not. Okay? We're going to count the number that are in that state. Okay? That's great. Okay. So let's go do that. So we're going to count the number that are obese, and let's go click on this. And now we can see here's the prevalence of obesity in our population. See this prevalence of obesity? Yeah? See that?
Yeah.
Prevalence of obesity. That reports the number of people obese right now. Let's draw a little chart that shows that, right? Let's have a chart that shows the prevalence of obesity here. Okay? So to do that, let's go to analysis. Okay, who needs TA help? Okay, TA help. TA's deploy. Okay. Okay. It looks like the TA is taken up. So yeah.
Oh, the whole
And then it says
Yeah. Okay. Who else needs TA help? Okay. Okay. So the prevalence of obesity, folks, was shown associated with the. I went through that a bit quick. Associated with the population. Here. You know. See that? Now, how do we do the fraction of the population that's obese? How would we do that? Well, we could do this. You know, fraction obese. What would we have to do? Well, what we could do is we could take an average over the population. Well, probably a better way to do it. We'll do a sum up over the population of 1 over the population size. Population dot size. 1.0 divided by population size, and we'll sum up the same thing. So we sum up over all those that are obese. For each of them, we count the fraction of the population represented by that person, by that single person. Then we will get the fraction of all people that are obese. Okay, so let's run that, and here we go. There we go, and there we go. Okay, so let me show that again. So this is what I did. Under this, I did fraction obese, so I added a new statistic. The expression was this, so expression is that. Okay, I did a sum. I did a sum here. And the condition was the same as the previous condition. Item dot weight state chart dot is state active, just like that. That's the condition.
Is there a reason for specifying the conditions?
What's the
Reason for the conditions?
Oh, the condition is which people do you want to count? This specifies the condition under which you count someone. Great question. So you're counting people who match this condition. What does this condition mean? It means, is the person named item obese? In other words, and how do we determine that operationally? We ask, is this given person, we consider it item. This thing is going to go through the population, person by person, calling each one item. We're going to say, for that particular person called item, for their weight state chart, are they in the obese state? If so, that's going to be true, in which case the condition will be true, in which case they'll be counted. If this is not true, in other words, they're not in an obese state, we're not going to count them.
But we didn't define item.
We didn't define item. That's defined for us, and you'll notice if you click here, it says item, the embedded object. See this? It actually says use item. So it's telling you, I already provide item for you. Item means the person in the population, in this case, the population member. That's what item is. So we can feel free to refer to that as item. And then we could say, hey, are they in this active state? Does that make sense? Yeah. And for this one, I did the same basic logic, but instead of summing it up, each one count as one, I count as 1 over the population size, because each of these is 1% out of the whole population. So if you want to total up what fraction are obese, each person, I am 1% out of 100, so I count 0.01 towards the fraction. And I just totaled that up. So if there's 10 people obese, you add up 0.01, 0.01, 0.01, 10 times, you get 0.1. That's the fraction. Does that make sense?
Yeah.
Okay, so this is the fraction obese, this is the prevalence of obesity. Those are two common ones, so I just wanted to show those to you. Do you want to see a chart of it? Super easy to do. Okay, let's go add a chart. Okay, so chart's going to live in main. It's not going to live in person. It has to do with the whole space. So go up to main, go over to palette, and let's drag in a chart. There's a thing here called time plot. See this time plot? So again, go to the palette. You go to charts, and there's a thing called time plot. You drag that time plot in. Okay? Okay? Drag in the time plot. Within the time plot, we're going to plot out fraction obese. Okay? Plot fraction obese. So how did we do this? I double-clicked on main, brought up main. I went to palette. I'm in the analysis area of palette. I dragged in time plot, and I want to add the data item. And I'm going to add a value. And what's its value going to be? It's going to be population dot count. Oops. It's going to be population dot prevalence. Excuse me, fraction obese. Okay. So this is what I'm doing here, folks. I went to the palette. I went to the chart area. I dragged the time plot in, and here I said add data item, a value, and I say population dot fraction obese. That's going to show that then on the chart. Okay. Okay, and I'm going to give it a nice title, fraction obese. Okay. Okay. So let's go run this. So first of all, let's build it. It's happy. Who needs TA help? Wow. Okay, there's the fraction obese over time. Okay. So that's the fraction obese over time, as shown by this chart. Any questions on that? Do you want me to show that again, the chart? Okay. So what did I do? I went to main. I went to palette. I went to this analysis. I dragged this chart on, this time plot. And then I went and I did add data item. I selected, I told it I want to do a value. What value? Well, I'm telling, hey, from the population, ask about this statistic. This fraction obese, that's the statistic we defined? That was the statistic we just defined. Remember that? We went up to this and we defined the statistic for fraction obese here.
And you have to use open and close parentheses because actually that statistic is itself a function.
That's right. That's right. So you have to do here population.fraction obese. Population because this is the name of the population. This is the name of the statistic, and you're actually calling it as if it's a function. It returns a value. And it's a value, you say it's a value here. And that will actually show you this this plot here that shows the number obese over time. Okay? Okay. So who has questions about that? Oh, okay. So, when we're I'm trying to think of a good example. So, if you were in when you were doing trigonometry early in life, or when you were doing things in Excel, if you want to ask about a so-called function like sine. Like the sine of 90 degrees, right? You would write it like that, right? So you put the parentheses around. This is called the function, and this is the parameter to the function, the argument to the function. So you say sine of 90 degrees, or you say, you know, the tangent of 30 degrees or what have you, right? And this is the same sort of thing. You're just giving population dot the name of your statistic that you define. If you define a statistic called, you know, prevalent cases, you would just call it like this, and this is telling it, hey, call this function. It treats the statistic like a function, as if it's assigned, but it's if it doesn't need any so-called argument. It doesn't need anything here given to it. So you're calling it, and it's going to return a value for that. So it's a matter of saying, okay, you need to call off to this thing, and it will give you back a value, just like sine will give you a value. This will give you a value back. Does that make sense? Okay. But the key point here is, folks, that this chart depends on this statistic that we defined up here, and we can define arbitrary statistics here. We could ask for the fraction that are underweight or whatever, normal and underweight. We can define our own one, and then we can create a chart which depends on that and shows it over time. Okay? Okay. Okay, so those are statistics. Okay, the final thing I want to do with this little exercise is to actually create a second state chart that depends on this first one. Okay, so how would I define a second state chart? Tell me what to do. Where do I go? Sorry? Okay, so yes, it's with the state chart here. And what do I drag in first, typically? The entry point. And we're going to call this diabetes state chart. Okay? I get a lot of questions about this from students, so I just want to make it clear how you have two state charts that interact. Diabetes state chart. And suppose we want a normal glycemic state. For simplicity, we'll make it normal glycemic, so that's non-diabetic, and then diabetic. Okay? So we're going to create non-diabetic and then diabetic, and we're going to have a transition between them, unfortunately one way. Okay? And this is developing diabetes, and we'll show that as the name. Okay? Questions for TAs? TA question. Okay. Okay. So that's good.
Double click this.
Now,
So it doesn't know what population.
we have, now let's associate with this transition a rate to go from normal glycemic to diabetic, a rate of 0.01. Okay? A rate of 0.01. Oh, I forgot to say, I'd like this model to be, the time unit to be in years. These are 0.01 chance per year. How would I do that? Does anyone remember where I specified the time unit in these models? We saw it before, a long time ago, like this morning. Where do we see the time unit? Does anyone remember? It's associated with the model itself. So we'll go up there and we'll specify for the whole model, model time unit will be year. Okay? Okay. Okay, so let's run this model.
What was the transition type you chose?
0.01.
Rate?
Oh, rate, yeah. So here we go. We have this prevalence of obesity being shown. Let's go suppose we wanted now to have a statistic that counts up the number of diabetic people. How do we do that? The silence is deafening. How would we total up the number of diabetics? Where would we do that? Where would we total up the number of diabetics in the population? Population. That's right. And then in statistics, right? And we could do prevalence of diabetes. Okay, so here's the challenge. Should you choose to accept it? Tell me the formula to use here. Prevalence of diabetes. You've almost got it there. Just tell me what needs to be modified. Prevalence of diabetes. Is this a count? Is it a sum, an average, a min, or a max? It's a count. And what thing should it count? What's the criteria of counting someone? What's the thing that determines whether or not someone should be counted? What's that?
Item?
Okay, item dot.
Diabetes.
Yes,
Yeah.
yes. That's right. Better than the World Cup. Yes, it's diabetes state chart. Diabetes state chart. Dot is state active. Dot person dot person dot diabetic. Yeah. Exactly. You folks are getting it. This is great. Okay. Diabetes state chart. Now remember, auto can be your friend. Do control space, and it will actually take you down to diabetes state chart. Dot person dot diabetic. Boom. Done. Prevalence of diabetes, and then we'll have the chart. How will we make the chart show the prevalence of diabetes there? Folks?
Add a data item to the plot.
Yes. Great. Okay, so we go to the chart. We go and we do add data item. Is it a value or a data set? It's a value. We'll make it count diabetics. Okay. Maybe we should do fraction because this can be a different thing, but we don't have fraction. So, okay, what's the value going to be? Give me the formula for the value. So-called expression for the value. Good. Dot. It's called prevalence of diabetes. Okay. Good. And maybe for this one, okay, one will be blue and pink. Okay, great. Okay, let's run it. Okay, sorry, I should have taken more time with that so people could see this. Okay, who needs help? Help. Okay.
Prevalence of diabetes, that should be the name of the statistic.
Okay. Here's prevalence of diabetes. This is prevalence of diabetes.
Just one, go to name.
There we go. This is the prevalence of diabetes one.
This is the name.
For those who are wondering, in the statistics area, prevalence of diabetes, we did a count. Item.diabetes state chart is state active person diabetic.
We can just double click this.
So here, for the given person, we're asking their state chart, is the certain state active? Diabetic state. And then, for this, we just called their that statistic and population prevalence of diabetes. Okay? Does that make sense?
You can put a space in there.
Okay. Okay, so let's run it.
Try running it through that. Yeah.
Okay. Okay. So it ran. Okay. Here's the prevalence of diabetes shown up here in the population. We could dive down to this level This person is diabetic, for example. Their weight is changing over time. They're diabetic here. This person is normal glycemic. This person is diabetic, etc. Okay? By the way, folks, for those looking at the screen here, I want to parse a little bit what's going on. This is obviously showing for a particular person which state they're in. And remember, they're characterized both by their state with respect to weight and their state with respect to diabetes. They're a given person. They have some particular weight, and it falls into one of several categories, and some particular condition vis-a-vis diabetes. They're either normal glycemic or diabetic. And so this gives that classification. This, what's in blue, shows what's the next transition that's going to fire here, and how long it will be until that transition fires. Now, something could end up overriding it, but right now they're going to next become overweight. They're in the normal glycemic state. Now they're overweight. And the next thing was going to be shedding it. And so they go back and forth between those states. Okay. So they're in these two states, one of those two states right now. Okay. Okay. Okay, the final thing that I'm going to do with this, the final thing, is we're going to make these state charts interact. And specifically, folks, someone's weight status is going to affect their chance of developing diabetes. Does that make sense? So if they're in a certain weight category, it will affect their chance of developing diabetes. So, folks, before we set someone's color by a variable, so depending on which state they were in, they had a certain color. How could we do something similar based if what state they're in, their weight state, determines their hazard of developing diabetes? How could we do that in a similar way? Anyone?
Outline.
Sorry?
Change the outline.
Change the outline. Okay, so not sure, but outline meaning?
The weight of the line or the color of the line.
Oh, okay. Yeah, you could predict. That's an interesting point. Right now, they have a certain chance per unit time of developing diabetes, 0.01. Suppose we wanted that chance to depend on what state they're in.
Arrows? Just arrows.
Okay.
Arrow with the weight.
We have a weight. Oh, okay. You might think there's an arrow. Turns out that we can actually change it if, just like when we change state, they change their color. When they change these states, we can change their hazard of developing diabetes. So all we need to do is, just like we had a color variable that changes here, we can add a variable that's diabetes hazard. And when they go and become overweight, their diabetes hazard, their chance per year developing diabetes will be different than when they're normal glycemic or when they're obese. And that will end up being the hazard that affects that. Okay? So that's the last thing we're going to do here. I think we've gone a little bit, pushed the envelope a little bit too much today. And we'll try to peel back from that tomorrow. But let's add that final bit in. Okay? So, folks, how would I add a variable in here? It's under General. Add a variable. Okay? And I'm going to call it diabetes hazard. And, folks, this is going to be a number like 0.01 or 0.05 or what have you. What do I make that? Is that an integer? Is it a double? Is it a Boolean, a true or false? Is it a color? What is it? It's actually a double precision value. I just leave it like that. I'm going to make its initial value 0, but when they come into this state, I'm going to make it diabetes hazard equals 0.01. Actually, I'll make it even half that, 0.005. So, folks, I created a diabetes hazard variable. How did I do that? I went to general, I dragged it in, diabetes hazard. Okay, I then, when they come in here, I want it to be set to 0.005. Okay, just like that. Does that make sense? So what that means is, as long as they're in that state, they're going to have a certain chance of 0.005, a 0.5% chance per year of developing diabetes. When they become overweight, we're going to have that chance go up to 0.04. Okay? So when they're overweight, the diabetes hazard will be this. It'll be 8 times as high. And then finally, when they're obese, the diabetes hazard will be 0.1. Okay? So now, the final thing, what do we need to do? So when they enter the state, they'll have a certain diabetes hazard, chance per unit time, 0.05. Here it's 0.4, here it's 0.1. What's the final thing we need to do to make that happen, make it operational? Yeah. So here we need the rate to depend on diabetes hazard. So now, folks, if you think about this from the perspective of survival analysis, there's a hazard function, and the hazard function is sort of changing over time as they change these states, and their chance of developing diabetes per year depends on which state they're in. As long as they're overweight, their chance of developing diabetes is going to be higher, for example, than their per year chance of developing the normal weight state. So this chance, the chance of going down here will be different now depending on what state they're in. Okay? So who needs help? Help?
One question?
Yes.
What were the variables, the values of diabetes hazard for each state?
Okay, for normal and underweight it was 0.5%, 0.005 per year.
Yeah.
For overweight it was 0.04, and for obese it's 0.1.
Okay.
Yeah? Okay. Okay. Great. Okay. Right. Okay. So let's now build it. It's happy. Let's run it. And so now we have this situation where people's weight is going to be a potent risk factor for their development of diabetes. But we really don't have a depiction of the number of diabetics right now visually. We could see the count of them here in the population rising, but we don't really have a visual representation. Suppose we wanted their visual appearance to depend on whether or not they're diabetic. How do we do that?
I'd say change the line color.
The line color, okay. So if they're diabetic, let's make their line color be red, otherwise be black. So what would we do? We would ask, how would we ask them, are you diabetic? How would we ask, am I diabetic? How do we know if they're diabetic here? We will use the question mark. It's exactly right. Diabetic. Okay. Okay, but what about diabetic? We want to ask, are we in that state? Who do we ask, are we in this state? We ask the, yeah, it's the state chart. It's the state chart. In this case, it's my state chart. So we're inside myself, so I don't actually have to worry about being explicitly specified. We'd say the diabetes state chart. I'd ask my state chart, hey, is state active? And I'd ask, is this state active, diabetic? If so, I'm going to make it red. Maybe I should make a different color, because red means something different right now in the other one. Maybe we should make it orange. Maybe what if we, blue? Otherwise, let's make it black. right? Something like that.
Or just make it null or something. Is there a null?
Or we can make it white. No, there's,
White would be weird.
okay, yeah, that's true. Well, it'd be kind of invisible then. But,
Except where they overlap, right?
except where they overlap.
I
That's,
guess you just change the language.
yeah, that's true. Okay. Okay, so let's run this. Okay. There we go. Okay, so now what we have is a situation where diabetics are shown in blue and non-diabetics are shown with white borders, and we have individuals' weight status coded by red, green, blue, yellow. Okay. Whew. So let's try to reflect a little bit more generally on what we've done. I've pushed the envelope a little bit too much in this exercise, but we've learned a fair bit. First thing that we've learned is that there are these various types of transitions, and I specifically want to refer you to the types of transitions which apply. Here's a list of AnyLogic's transition types. So we have a timeout transition, a fixed rate transition, a variable rate transition. Where have we seen a variable rate transition in this model? Anyone? The diabetes hazard was variable rate. Here it changed over time. Depending what weight state we're in, our chance of developing diabetes differed. A fixed rate transition, where you have a certain chance per unit time of going from one state to the other. A timeout transition, entering the state you at a certain time, after a certain time exactly you'd leave it, and that time could either be specified as a number or drawn from distribution if you wanted a custom distribution. One thing we haven't looked at yet, but which we'll be seeing, is a message received transition. A predicate transition condition, we only transition when something is true about the model, or when we reach a location. If we're going to see if we travel, we can reach a location. Okay. Now, moreover, we can have these branches, and we haven't really shown this here, but we see it illustrated here. There can be a branch that allows us to say, okay, we'll go down here, we'll go this way if a certain condition is true, or this way. And related to Ben's question earlier, if someone was exposed to a pathogen, for example, they might get infected with a small chance, say 0.05, and 95% chance they just remain in the susceptible state. So here they get exposed, and they have a certain chance based on exposure to stay in the state they came from, otherwise they continue on to a different state. This is for TBs. They either go to a latently infected state or develop active TB directly. So these are branches that you can put between these states to kind of route them based on a conditional basis from one thing to another. These are very useful. The other place that these are useful is for the initial state of the model, because often we have models where we want some people to start in one state, other people to start in another state, often based on some empirical distributions, in which case, where would you put these guys if you wanted that? If you wanted the initial state of people, if we wanted people to start not just all normal and underweight, if we wanted to start some this state, start that state, how could we do it with one of those branch transitions? Anyway? If we wanted some people to start here but others to start here at the very start of the model, what could we do?
The entry point.
Sorry?
The entry point.
Yeah, the entry point. Rather than having the entry point just go to one state, we'd have it instead go to a thing like this, like a branch, and with that branch they could go this way or they could go that way. We could have two branches. Actually, you could divide it in three, so this one branch could go to each of these states if we wanted to divide people. Okay? So that's a very common way of doing that. Not the only way, but it's a common way. So this is just a very simplified way where everyone starts in the state. In general, we'd start them in different states. Okay? So you know, broadly we use these different transition types in different ways. One way is, like with a fixed timeout, if we have people aging out of an age category, let's suppose we have, I work a lot with age-specific data. So, for example, we'll have, you know, the occurrence of diabetes in ages 0 to 4, and then 5 through 9, and 10 to 14, and we have very defined age categories. And sometimes we represent that aging process with state charts with fixed timeouts between them, so they go from one category to another. And some of the example models I've given you will include that. And then sometimes if you have natural histories of infection or other things, you have tightly defined time constants. You might do that, and you might draw the amount of time till the timeout, till you leave the state. You might draw it from a distribution. So you get a custom distribution, a beta distribution for how long you spend in that state. It's a timeout with a value after which you leave being drawn from a distribution, drawn from some empirical data. Okay. So, for example, we could have a timeout that's, you know, occurring after a fixed period of time, and we can associate an action with the timeout. Okay. So, if we wanted to, when they make that transition, we could print something out, report to a database, or something along those lines. Yes.
Can you check the status of your Dropbox upload?
Oh, sure.
It doesn't seem to be.
Okay. Okay. Oh, yeah. It encountered a problem. I keep on getting kicked out of the local wireless, so we'll have to check it later. Okay.
I've signed on to one that's stable.
Okay. It's my, yeah. Sorry, folks. I'll okay.
Yeah, the web one.
Okay.
Connect from Wi-Fi and then just sign into the web one, and it should be fine. There's no sign in or anything required.
Oh, okay. Okay. You think it'll work for that?
Well, it works in mine.
Okay.
It's already linked, so.
Okay. Right. Okay. I'll give it a try then.
Sorry.
Okay. I'll quit Dropbox and reconnect. So come on. No, I don't want that. Oh gosh. Exit. Boom. Okay. Sorry. Dropbox. Okay. I give it a try, Kurt. Okay. So. Oh, yes, we have exit points in here. So one thing within AnyLogic, you have these final states, and those can be shared between multiple state charts. So for example, if there's someone going to some common state, this will mark a place where you're no longer in any of these states, but outside the condition of the state chart. So you can have this final state, commonly used for something like death, or a state where none of these states apply anymore. Right. This is actually a fairly important point. Within a given state here, you can actually define what's called a self-transition, and that transition occurs from the state into itself. And you can associate that transition, nothing here, you're not actually, if it's inside of here, you're not actually leaving it, but you can get something happen with a certain frequency. For example, every one time unit you could print something out, or push something to a database. You can also do those sort of self-transitions out of the state and back in which case you're actually going out and re-entering the state. That's not a very nice one. But you're actually going out and re-entering the state. And that's actually useful in some cases if you want it to kind of, if you want to keep track of if you want to change sort of how frequently, to recalculate certain rates or something like that, you could do so by leaving it. I'm trying to position this. Yeah, something like this. It will actually leave it and come back in. Okay. And we may see that later in the week. You can have parallel transitions, multiple state charts, and you can have them interact. We've just shown that. Finally, although I'm not going to cover it here, you should be aware within AnyLogic you could have hierarchical state charts. In one of the models that we have, I'll actually just illustrate this, that we've provided you. It's a model that involves a zoonotic infection. There's actually significant use of this to simplify the logic associated with the model. So I thought I had it here. Let's see. Maybe it's not included in this, but I think this one has it, right? Okay. So in this case, we're going to have some states include other states. So this is going to be what's called hierarchical states. So for example, this state represents dialysis as a whole, and then within it you may go between peritoneal and hemo. And there's some transitions which will occur out of this state regardless of whether you're in peritoneal or hemo. If you receive a transplant, you'll go to this other state of being in a transplant state. And so here, rather than having separate lines from this one and from this one to this state, we just create a line from the surrounding state. And so similarly, you can put several states embedded in others, and that just simplifies the logic. You don't have to have transitions from every single one of the internal states, just from the outer state. So we have these outermost states and middle states. Okay. So I think that's all. I ask you for your patience. I thank you for your patience with this. We went very aggressively, probably too aggressively with that last example. But what you have seen, I hope, is eye-opening in the sense that you can have multiple state charts that interact. One state chart can depend on its dynamics on what's going on in another state chart, and vice versa. You can have that reciprocal causality where things here affect this and things here affect this over time. That's an important point because that's hard to capture in many types of modeling. Secondly, we've seen how AnyLogic supports in a fairly declarative way two important features, namely, number one, statistics. So associated with the population, we can go define statistics like the prevalence of obesity, and without writing a lot of code ourselves, we can tell it, sum up people match this characteristic. Just count them for me. Or sum up this thing which represents a fraction of the population who match this characteristic. By doing that, by having those statistics, two good things come about. Number one, when we run this model, we can interactively go and see the value of these statistics by clicking on this population. And so you see as this model is running, these statistics are updated. We could see the prevalence of obesity or the prevalence of diabetes here within this context. And that's useful. The second thing that it gives us is the ability to very easily create charts which depend on these statistics. And specifically, we saw that creating a chart in AnyLogic is very simple. We don't have to write a lot of code to do it. We drag in something from the palette associated with this analysis, namely time plot, and we tell it, hey, go add data items. And these are both data items that depend on these statistics. So by defining statistics for the quantities of interest, we can get reporting of those quantities, both when we're running the model in terms of the numbers, and secondly, in terms of a graphical representation associated with charts. We can label these charts accordingly, have multiple charts, and it will be plotting it out as the model is running the quantities of concern. Often in a model, you'll have many of these so-called observer processes that collect information about what's going on in the model. Later in this week, we'll be discussing types of observer processes. Sometimes you'll write it to a database. Sometimes you'll write a file. And there's guidelines that you should follow when doing this to make it reliable. But a very common way is while the model's operating, you have these charts running. You have data being printed out on the number injected, and this provides an easy way to do that. So we've seen how that also in AnyLogic is fairly straightforward. There's a lot of things here going on, but each little piece isn't too bad to sort of add these things in. And we can do it in a fairly, what we say, declarative way, in a way that doesn't require us to specify too much of the how, just specify what we want to collect, and it will take care of putting it into the chart, etc. Okay, those are the components which I tried to bring across in this particular exercise. This was aggressive as an exercise, probably maybe the most aggressive exercise of the boot camp. But it brings home some basics about state charts and how they can interact and with reporting that I hope will be helpful. I think we'll leave that it's the last hands-on exercise today. We'll have more hands-on exercises tomorrow where we'll build on our knowledge. But we can put these away. We do have very similar models available for you in Dropbox if you want to look at them. What I'd like to do for the next hour is I'd like to suggest that we talk about possible project ideas that we could then explore in the course of the week. If there are some of you who are quite certain you are not so interested in projects, there are a wide set of step-by-step tutorials which will walk you in great detail through building models. There's also challenges, and finally there's the actual lecture slides which you can look at and solutions to these little exercises we did in class. Maybe I'll take a bit of a break by getting a bit of water, but if people would like to talk about project ideas, what I'd suggest is that you maybe put your name on a board here and maybe put topic, your name, and then other people can put their names up there who might be interested if they're interested in a similar project. And Kurt, Winchell, and myself will come around to you and talk about your modeling ideas, sort of what you're interested in, the topic, and then we'll try to put together a little plan how over the next 4 days, so by Friday, we'll have something in hand for you to go back with in that area that can be built up incrementally. So we can build it in a way where you learn step by step along the way, build your strengths related to the material that's presented. So if you could put your name put the topic and your name, and other people can add to that, and then we'll try to come around to each of the groups. Okay? Now, May, I know that you had mentioned something that may be possible to have another room, but should we plan on doing it in this room for now?
Yeah, I'm not sure if, we might have to do it here for now.
Okay, that sounds great.
Let me check and see.
Sure. So yeah, just we'll yell out the names and you can direct us to your appropriate groups. Okay. And if you have questions as well, I think you can grab us if we're not devoted to a particular group. Okay. So thanks very much.